Good morning, good afternoon, as the case might be. Welcome to this edition of the webinar series on applied analytics success stories. My name is Rajesh Tyagi, and I'm the organizer for this webinar series. Now, this series is an initiative of the Informs Practice session. And before we go on to the speaker, let me just spend a couple of minutes talking about this section. The purpose is to The purpose is to support and advance the practice of analytics, operations research, and management sciences. Um, it sponsors 3 annual competition. In fact, 2 of them were just held earlier this week itself. Then we also have 3 items in the red font, as you can see. These are more of the monthly series. So the first one is Applied Analytics Success Stories, where we have speakers talk about real world applications and they talk about their success stories with those applications. So the next one will be on May 21st. The second series is a new series, Sustaining Outstanding Analytics Organization. Here we will have speakers who will talk about the analytics organization, how it is set up, what kind of projects they work on, and what kind of people and skills are they looking for. And the first one in this series would be on May 7th. This is with Chevron. And we also have a monthly virtual network happy hour. The next one will be on April 30th. This is a little bit more relaxed setting. The topic varies. For this next one on April 30th, the topic would be basically a debrief from the virtual conference that took place earlier this week. On to the webinar. The topic today is predictive models for optimizing imaging decisions for detection of metastatic prostate cancer. And we are honored to have Dr. Brian Denton with us. And Dr. Benton's research interests are in data-driven sequential decision-making and optimization under uncertainty with applications to medicine. He is the chair of the Department of Industrial and Operations Engineering, and he has a cross appointment in the School of Medicine, both at the University of Michigan. Prior to that, he worked at IBM, Mayo Clinic, and North Carolina State University. He has co-authored more than 100 journal articles, conference proceedings, book chapters, and patents. He's past chair of the Informs Health Applications section and past president of Informs. Quick note here that for viewers, you will see a Q&A button on your screen, and you can always use that to submit your questions, which will be answered after the presentation. And we will also have a networking session following it. That means from 1 to 1:30 Eastern time. And typically the Q&A session will continue onto the networking session. So we'll have sufficient time to answer all the questions. I will now hand over to the speaker. Welcome, and all yours, Dr. Denton.
Well, thank you for a very nice introduction, Rajesh. And I'm just going to try to share my slides. So I'll see if we can do that before we get started. And so I'll ask you if you can still see those.
Yes.
All right, great. And let me just set up one more thing. Okay. So thank you very much for that great introduction. Thanks, Rajesh, for organizing this. And thank you, Beth West, who's on the call here from Informs, for your help with this. I took notice of this series some time ago, and I thought it was such a great idea, and I was really humbled to have the opportunity to present in it. So I hope I will keep you interested, and I look forward to some Q&A afterwards. So I'm going to tell you about a project that has been going on for a long time, as far back as 2013. So there's an interesting storyline about this project, and I'm not going to stick too much to it, but I am going to talk about a few of the things and how we overcame some of the hurdles and challenges of implementing some of the work that we did. Before I start, too, I want to point out that this is a very cross-cutting collaboration that included, of course, operations research and analytics types like me, also students, PhD students, and some undergraduate students who did a lot of the work. So I'm lucky to be here to be able to talk about it, but there's lots of credit due to the whole team. We also had clinical collaborators involved very significantly. None of this would have been possible without all of their help along the way too. This is a project that is ultimately sponsored by Blue Cross Blue Shield of Michigan, and was a project that was part of a collaboration called MUSIC, which is the Michigan Urological Surgery Improvement Collaborative. And so I'm going to tell you about this. These are quality improvement collaboratives that we have a number of them, about 12 in the state of Michigan. Some other states are developing them as well. And the goal is to try to improve healthcare in a variety of important areas. And so this particular project that I will talk about is about trying to detect metastatic prostate cancer in men who have been diagnosed with prostate cancer. So that's a little bit of the background. And I'll see if I can. Here we go. So the context is men who have been diagnosed with prostate cancer. So everything I talk about relates to people that have already been diagnosed with prostate cancer. And that diagnosis is done using biomarker tests and ultimately a biopsy to try to detect the presence of cancerous cells in the prostate. Once that happens, then imaging is a very important part of staging the cancer. And specifically, imaging is used to determine if the cancer has spread outside of the prostate, so if it's metastasized. And that's important because the course of treatment would be very different than if it was localized to the prostate. So two very commonly used forms of imaging are bone scan and computed tomography, or CT scan. I'm sure you've heard of CT scan, maybe you've heard of bone scans. These are non-invasive, but they do come with some harms associated with them. For example, radiation exposure for CT scan. They cause a lot of anxiety for patients because they're going to, they know to determine whether they have a cancer that may have metastasized. Of course, it takes time and they're expensive resources that can be used for lots of things, not just prostate cancer. So that's a little bit of background on the two imaging modalities. And there's two ways of looking at this. One is that there are significant harms associated with missing a case of metastatic cancer. Fortunately, metastatic cancer in patients with prostate cancer is rare relative to the number of people that get prostate cancer. So one message you'll hear me talk about during this presentation is that prostate cancer isn't one disease. There are many kinds of prostate cancer. Ones that would be best just left alone and you'd be better off not knowing about them, and ones that could be lethal and need to, or rather benefit from early detection. So what happens if you miss somebody, a patient who actually has metastatic cancer? Well, that can impact the treatment decisions that are made. So when cancer is contained to the prostate, it could be removed, for example, and that's called radical prostatectomy, and that's the most common type of treatment with curative intent. So you could literally cure a patient if you remove that cancer. But if it's metastasized, you won't benefit from that kind of treatment. Chemotherapy would be more appropriate. So if you miss a cancer, you may subject a patient to a substantial surgery that can impact their quality of life, has a long recovery period, and they wouldn't benefit from it. So the stakes are pretty high there. There's downsides to imaging as well, though, and this is the second part of the picture. And this has been described through the Choosing Wisely campaign that's developed. The ABIM Foundation is a foundation that promotes shared decision-making between patients and physicians to try to make the decision that's right for patients, acknowledging that there's not always a clear black or white answer. And so what's bad about imaging? Well, sometimes it causes harmful radiation exposure if you're talking about CT scan. For bone scans, there's often false positives. And so when clinicians look at a bone scan, sometimes they see, they're called hotspots or flares, and then they have to investigate those. More often than not, there's nothing there, it's an aberration. But the investigation involves doing a biopsy, like a bone biopsy, for example. So drilling into bone to take a sample. And it's painful. Usually there aren't any substantial long-term health impacts, but it's quite painful and anxiety-causing for patients as they wait for the procedure. And also, of course, expensive. Using imaging also, blocks access to important resources that could be used for some other, purpose. So if they're not, CTs or bone scans are not being done for patients that won't benefit from them, then that's going to shorten the wait list for patients with other kinds of conditions that could benefit. So this is an interesting problem, and you find these kinds of things all over medicine because there's a debate about what the right thing to do is. And I'm showing you some of the most well-known associations and studies that have weighed in on what should be done when it comes to imaging for men newly diagnosed with prostate cancer. So the European Urological Association, one of the largest in the world, has a guideline. The American Urology Association has a guideline. The National Comprehensive Care or Cancer Network in the United States has a guideline. And I'm listing one of the well-known studies done in Italy, actually, and quite a prominent study. And all of these are different. Right? So there's not one simple answer to what is the right thing to do. So when my collaborators and I got involved in this project, this was a key question. What should be our guideline for deciding which men need to get imaging and which men could avoid imaging safely? Very important question. Lots of debate, and if you looked at the data, some were roughly following, some physicians were roughly following certain of these guidelines. Some were doing things based on their best clinical judgment. There's just a wide range of the kind of approaches to how the decision to image was made. And so we were looking at trying to develop a consistent guideline and then incent clinicians to use it to improve the quality of care for men that are part of the Michigan Urological Surgery Improvement Collaborative. So overall, the objective basically is to find out, which patients should get imaging and which patients can safely avoid imaging on the basis of individual risk factors. So this is why we're using predictive models, because we want to predict what the likely outcome of a bone scan or a CT scan would be if you were to recommend a patient for one of these kinds of imaging tests. So I want to set the stage a little bit in terms of the Michigan Urological Surgery Improvement Collaborative. None of this would have been possible without this collaborative. It has developed over the last 10 years. It's a type of quality improvement collaborative. And so these are starting to sprout up in many states now. And I think the state of Michigan has been a leader in this area. And the basic idea is to have clinicians, in this case urologists, provide data on their patients from across the state. Our goal is to get to 100% all patients, having their data in a centrally managed registry. So it's a physician-led statewide collaborative. At the time we were sort of wrapping up this work, they had more than 90% of urologists in the state. And if you are familiar with the state of Michigan, this blue part is Michigan. Sometimes people describe it as a glove. This upper part is the Upper Peninsula. And so there are urology practices in more rural areas like this. There's a large concentration down in southern Michigan, including our own Michigan medicine practices here at University of Michigan. And data is collected from all of these practices. There's a whole process for evaluating the data, doing data audits to guarantee high quality data. So nurses are visiting to audit some of the data that's going into this database. And it's essentially providing almost complete perioperative data for men with newly diagnosed prostate cancer. So it's an incredible resource that's being used for all kinds of things, including this study. So I'm going to talk about various parts of this sort of end-to-end process of data collection. That was largely done through music. So from a point of view of analytics or operations research, we're fortunate to have excellent data readily available when we started the project. We developed some models. We did some model validation, and where this gets interesting is early on, we didn't have enough data to do prospective external validation, which would be the gold standard for models, such as the ones that we produced. But we didn't have that, so we had to do internal validation and tried to get to a point where we were comfortable enough that we thought that we could explain to the urologists and the practices who are ultimately the decision makers in music about what guidelines to adopt, how this worked, and give them some confidence in it. We didn't want to wait until we had all of the data. That would have meant several years of waiting for more data to be able to do a complete validation, and at the same time there would be harms to patients who are getting imaging that don't benefit from it. So there's a little bit of pressure there, a little bit of stress that came in as we were thinking about how to do the validation. There was a long period of implementation. I'll talk a little bit about that. And then we did post-implementation analysis and post-implementation validation, including external validation. So this is sort of like the story, of the project. Very took a long time to get to where we are today. And so the main things I'm going to tell you about are how we developed predictive models, how we validated them. Bias, statistical bias is an incredibly important issue here, so I'm going to talk about that and tell you one approach that people have used, quite easy to implement actually, and show you how much of a difference it makes when you're trying to develop models like this. And then ultimately we wanted to be able to classify patients into two groups: patients who should get imaging because they'll benefit from it, and patients that could safely avoid imaging. So that's where we're headed with the presentation. So the first part, prediction models for metastatic prostate cancer. Our big question here was, can we develop predictive models that are well calibrated, accurate enough to provide reliable predictions for newly diagnosed music patients? When we started the project, we didn't know if this was possible or not. So we used initially a very common approach for predictive modeling, multivariate logistic regression, to try to estimate the probability that a patient would have a positive bone scan or a positive CT scan. So we had a binary dependent variable. 0 represented, a bone scan that was not positive, meaning the patient had a bone scan and it didn't help them. 1 was positive, meaning it identified metastatic cancer ultimately. And then we used a multivariate logistic regression model to, first of all, we had to acquire some of the major risk factors, and this is a list of some of them here, not all, but some examples, and then proceed with validation. So you see things here like age, prostate-specific antigen. You may be familiar with that because it's been in the news a lot over the last 20 years, or you may not. It's basically a simple blood test, requires a needle to collect a blood sample, and then the test involves determining how much of a certain protein, it's called prostate-specific antigen because it's expressed from the prostate, and the amount of it in the bloodstream is correlated with the presence, in this case, of metastatic cancer. But it's not perfect by any means. There's also a tumor stage that comes into play. Gleason score you may not have heard of. That's a scoring system, a discrete scoring system that's going to categorize patients into essentially low risk through high risk. And it's determined by a pathologist looking through a microscope at cells extracted by biopsy to determine what the structure looks like, and then they render a decision about the Gleason score. And we looked at other things too, like percentage biopsy positive cores. What does that mean? Well, what that means is that when you do a biopsy, a series of hollow core needles are used to sample the prostate, see if you can hit a tumor. So it's most common to have 12 cores now. If you have one of the cores showing that there's some cancer cells, then that might indicate a lower volume tumor. If all 12 come back with positive cores, then that suggests a higher volume tumor. Again, not perfect. This is not a perfect estimate of tumor volume, but it's got some signal to it. So we started this project back in June of 2013. The collaborative was getting going. Not all of the practices were part of the collaborative yet. I think they had about 20 signed up at the time. And you can only collect data as quickly as it is generated through the passage of time. So we had 416 patients at that time who had received bone scan. Relatively small sample size. We deemed it suitable for developing a model, but it certainly wasn't possible for us to use a holdout sample, for example, of 50% of the patients to test the model on. So that's where the internal validation comes in. And we'll talk about that in a minute. We moved on to CT scan, looking at that a little later, and by September, a lot more data had been put in the system as they were building it up. We had 643 patients who received a CT scan. Still not an enormous sample relative to the number of positive cases. So internal validation was really important here to decide if and how to move forward using the models. Of course, at this point, in June 2013, we didn't even know if you could predict anything useful from the data. This is a typical table that clinicians, when you publish in a medical journal, would require. It's called Table 1. It tells you a little bit about the population of patients. What I'm showing you here are, we screened a large number of factors by doing a univariate analysis to see what's associated with the occurrence of a positive bone scan or positive CT scan. And we lifted up the threshold, I think, to about 0.1. You would often hear p-value thresholds of 0.05. These are, of course, to some degree arbitrary, but low p-values suggest that there may be some association there. And we incorporated these factors into the multivariate logistic regression model that we developed. So you're seeing some of the things I mentioned: age. We use log PSA because it's highly skewed, has a very long tail. So we use the transformation there. Gleason score. I won't go through all the details, but these are important factors that urologists look at when they're deciding what to do and whether to image. So I mentioned we did some internal validation. There's different approaches. We actually used cross-validation and bootstrapping. We decided bootstrapping was superior, and we used that on the development sample. So when I say development sample, I mean that data, those 416 patients that had bone scans. We applied bootstrapping to try to get a sense of how well things would validate with respect to optimism bias. And so optimism bias, this is something that happens. You're probably familiar with the idea that if you fit a model on a data set and then you test the validity of that model on that data set, you get a biased estimate. So we wanted to test the model on an external data set, but we didn't have it, so we used bootstrapping to try to estimate optimism bias. Later on, as we collected more data, we were able to do external validation. Okay, so this is some of the timeline of sort of how we were moving through the project as data was being collected. Maybe in a simple world where we didn't worry about patient health, you could just wait 5 years until you had enough data to do everything, but that really wasn't an option for us. So how does bootstrapping work? The basic idea is we have an initial cohort on the left, top left here. 416 patients for bone scan, for instance. And for bootstrapping, what you do is you generate sample cohorts by sampling the initial cohort with replacement. Okay, so you're sampling with replacement, and you typically sample at the level of the number of samples that you have in the initial cohort. So we would sample with replacement 416 patients to create a testing cohort. And we did this many times to generate a number of these. And then we would test the bootstrap predictive model. And we would look at the test performance on the initial cohort and then on each of the bootstrap cohorts to get an estimate of the test performance for the bootstrap model and the apparent performance on that model that was built on the bootstrap sample. So if you take all that, put it together, remember we're doing it for a bunch of different cohorts that we're sampling with replacement. So if we do M iterations, we've got M models that we've estimated, and we get an estimate of the optimism, and then we can take an average over the number of iterations of bootstrapping. And so the optimism estimates used to update the apparent performance of the model. So whatever that performance measure is, and I'll show you a couple of examples, the validated performance would be the apparent performance minus that optimism bias. So we looked at a few different performance measures for the models. Two that we took a very close look at give you different views of what's happening. So we looked at discrimination as one measure of how well the model works. And by discrimination, I mean how well does it differentiate patients newly diagnosed with prostate cancer into two groups, one that should get imaging and one that doesn't need to get imaging. And so I'll talk about a measure of discrimination in a moment. So that was very important for being able to classify patients. We also wanted to be able to use the risk models to give estimates of the actual risk itself. And so we have a website that we developed called Ask Music. And in the Q&A, I'm happy to pop it up or send you a link. The idea is that urologists can sit down with patients and look at the models and look at the actual risks and consider a decision about what to do based on their risk perception or their risk aversion. So different patients are going to have very different perspectives on questions like, is a 1% chance of having metastatic cancer high or low? If you ask 100 patients, you'll get very, very different answers to that. And there's no really right answer as long as patients are informed. So with calibration slope, this is one of the things. So there's multiple ways to look at calibration. So this is how we measured how well the model predicts risk. And so the calibration slope is one popular way to do this. If you were to measure calibration on the data that you use to build the model, you would get that it's perfectly calibrated. If you measure it on an external data set, you'll generally find that it's not perfectly calibrated. And the way this works is you can think of it as looking at whatever that linear predictor is, in this case from our logistic regression model. What we're going to do is fit a new model that's a linear function of that. So there's going to be a slope beta and an intercept alpha. If we did this on the test data, we'd find alpha equals 0, beta equals 1. When we do it on external data, we find a difference there. And so I'm going to show you some examples of validation that we did after we had enough data to do some more external validation and how it compares to our internal validation. So this table is showing you, in a way, like the passage of time in terms of the story of this research project. So on the left, I'm showing you ROC, area under the ROC curve. So if you're not familiar with that, ROC stands for Receiver Operating Characteristic Curve. And it plots sensitivity versus 1 minus specificity. For historical reasons, it's 1 minus specificity. I'll tell you a little bit about sensitivity and specificity for those that are not familiar with that term in a few moments. But the main thing to know is that these values, they vary from 0.5 to 1. 1 is perfect. 0.5 is a useless model. It's like flipping a coin. And so what we found here, and I think I'll just focus on this measure of discrimination first. So the area under the ROC curve, under our internal validation, 0.82 for bone scan, 0.87 for CT scan. It's considered very good. Now this is around 2013. We didn't have these numbers over here with external validation, okay? But we had done some work to validate these estimates using bootstrapping, and they were deemed to be quite good, and ultimately we decided to move forward using these models. Later in time, when we have more data, so the 664, these are 664 new samples that we obtained after the models were developed, so there's no risk of contamination of the results. We get a very similar, actually, like we were quite surprised, very similar, 0.81 ROC, 0.86, so just small degradation. If we look at calibration slope, again, closer to 1 is better. We got good calibration, indicating that the risk estimates we're generating are good, even better for CT scan. In external validation, we actually found, and we have some hypotheses about why this is the case, but actually the validation was even better in that case. And again, that was a surprise. But we didn't know that when we were working with the internal validation. So it was something we were very concerned about and trying to do everything we could to make sure that we weren't taking on significant risks by implementing a model that wasn't prospectively validated on external data. I think I'll skip over. We looked at a lot of different kinds of ways to validate the model. We were obsessed with it for a period of time because we knew we were thinking about implementing it, and I think everybody on the team wanted to be very comfortable with this. So now I'm going to switch to bias-corrected performance of imaging guidelines. So I told you that bias is an issue. There's a systemic bias that results, called verification bias, from the fact that not all men in our data set received imaging. If everybody got a bone scan and everybody got a CT scan, that would have been much easier for us. But that doesn't happen because urologists, some are following national guidelines, some are following their clinical judgment, and not all patients go for imaging. This could be a really serious problem because if you build a model only on the patients that got imaged, they're naturally higher risk, and so you end up with seriously biased estimates. So I'm gonna talk about just briefly about an approach that you might put in your toolkit if you're ever having to predict a binary outcome and you're worried that your population isn't representative of the true entire population because you don't have data on some kind of, it could be a diagnostic test, it could be a survey, it could be sample data that's collected on a shop floor, for example, if you're talking about a manufacturing context. So to do that, I'll just introduce a couple of pieces of notation here. G is going to represent a guideline. So like the American Urology Association guideline, as an example, determines, the idea is to determine who needs to get imaged and who doesn't. So G plus is going to indicate when it's positive, meaning that the patient gets imaged. G negative indicates when it's negative, so the patient's not going to get imaged. Now I've talked about sensitivity and specificity. This is something that's talked about all the time in medicine. If you took a clinical statistics course, you'd be talking about this. Some of you might be more familiar with like type 1 and type 2 error, which is very analogous to this. There's a direct connection between them. But the gist of it here is that in our case, sensitivity is going to be the probability that the guideline think of the guideline as a test of whether a patient should get imaged. The probability that the guideline is positive given the disease is present is sensitivity. The probability that the guideline's negative given the disease is not present is specificity. And you want these both to be 1. You know, that's what you want, but that's never the case. You can never get that. What you want is for them to be high in practice. When we estimate these, though, without accounting for bias, we get vastly different results that are actually useless relative to the decisions we want to make. And I'm going to show you some data that backs that up in a moment. But because not all patients in the cohort receive imaging, it leads to this notion of verification bias. Okay, so how do we correct that? Well, first, maybe just an image that kind of hopefully, if it's not clear, makes it very clear. You know, the entire population for us, that's all patients diagnosed with prostate cancer in the state of Michigan that we've got data for. If you think of patients, and this is an extreme example to make a point, but the number of patients, red patients are ones with metastatic cancer, blue patients are ones that don't have it. And if you look only at the patients that received imaging, you're going to have a higher portion of those patients with metastatic cancer compared to those who didn't receive imaging. We're going to have a much lower portion. So that is a very real issue if you're trying to estimate and validate a good predictive model. So the verification bias correction approach is actually incredibly easy to implement. You have to go a few steps to understand why it works and under what assumptions it works. But it's very easy to implement. All you need to know is Bayes' rule for this. So once you are comfortable trusting it, and you can look at this paper by Begg and Greens on this that goes into some of the conditions around this. For those of you who are very interested in this kind of thing, the main condition is that the missing data should be missing at random. There's a distinction between missing completely at random, which would mean like, say, flipping a coin to determine who's got imaging data in this case. Missing at random means that you can predict things based on the risk factors. So it's not a strong assumption as it seems. And the idea here is, you know, when you want to, let's say for sensitivity, we want to estimate sensitivity. We can recast this, all right, using Bayes' rule, and then we can estimate the probability that the disease is present, you know, given the guideline is positive, using the entire population. How do we do that? Well, we use that risk model that we estimate on the imaged population. We can also estimate the probability that the disease is present across the entire population. And then estimating the probability that the guideline is positive, that's just a simple matter of applying the guideline to all the patients in the cohort. So let's take a look at some results. I know I moved through that fairly quickly, but I'm happy to talk more about this later. So I'm going to pick one example. There's a lot in this table that I can talk about, but I want to make one point from this, and that's that verification bias is a very important issue. So these are the clinical guidelines I mentioned. Let's focus on CT scans. So we had the European Association of Urologists and the American Urology Association. I'll concentrate on the AUA since we're in the United States right now, or at least I am. You may have people from all over the world. But the results are fairly similar for the European guideline. So if we look at the sensitivity and specificity, remember we want these to be 1. In the uncorrected estimates, when we just use the patients who had imaging, we get extremely high sensitivity and incredibly poor specificity. And what's interesting is these results, they're just completely wrong, okay, because of that bias. When we do use bias correction, we get something that is closer to the truth, or at least we're much more confident it's closer to that truth. And this is substantiated by looking at least one study that was done in the past where all patients were imaged. It was a study done in Italy Things don't match exactly because that's a different population, but these estimates are in the ballpark. So if we had used these estimates, and seeing this is what actually led us down the path of realizing how important verification bias is in this context. But if we had used these, that would have been a huge mistake. Okay, well, I'm gonna change gears a little bit and talk about classification modeling for metastatic cancer detection. And our question here was, can we design imaging guidelines using machine learning methods that outperform the published guidelines? And in fact, we wanted to see if we could do better than the multivariate logistic regression model that we had developed. So depending on how you think of what machine learning is, that's a very broad umbrella of terminology, but often logistic regression falls under that umbrella. We tried other methods too, though, like support vector machines and AdaBoost, and we developed a method of our own that I'm going to just describe briefly. And I will mention that all of what I'm going to talk about is in a paper that's published in Operations Research. It was just published online, I think, a month or two ago. You can check it out. If you don't have access, you can come to my website, which has a clean version of it in its entirety. I'm relying on Beth not to report any kind of copyright violation here. Check it out. If you can't find it, just let me know. I'd be happy to share any of this stuff with you. So when we started looking at classification models, right, so the alternative ways for us to try to discriminate between patients that need imaging and patients that won't benefit from imaging. The two major challenges we have, one I've already talked about, is unlabeled data. By unlabeled, I mean they didn't get an imaging test, so we don't have that 0-1 label for those patients, and there are a lot of them. And then there's also the issue of imbalanced data. So there's a minority of patients, fortunately, that have metastatic cancer, a strong minority of patients that fall in that group. When you're building classification models, you need to be careful because sometimes the outcome, like a false positive or a false negative, could have very different costs associated with it. And in my mind, when I'm saying cost, I have the word cost in quotations, because I don't mean a monetary cost, I mean more like a harm to the patient. So the patient that has metastatic cancer but doesn't get an imaging test is harmed by not being able to proceed quickly to chemotherapy and perhaps have a surgery that's not going to help them. Versus the harm of somebody who has an imaging test but doesn't have metastatic cancer. Also bad, but not as bad, not close actually. So to address these, we used a semi-supervised learning approach, meaning we tried to use the labeled data and the unlabeled data. We used a cost-sensitive approach to apply different costs to those false positive and false negatives. And we also combined these approaches into one approach that's sort of a novel combination of ideas that others have developed over time. So this is the most mathy slide. I know it's a Friday afternoon at lunchtime, so I don't have a lot more slides like this, but I'm happy to talk more about this, and that paper in OR goes into a lot of detail. But the approach that we developed was one that uses, we call it a cost-sensitive Laplacian kernel logistic regression. And so what are we trying to do? We're trying to come up with a function that's going to be able to take risk factors, PSA, pathology information, age, and tell us which patients need imaging and which patients don't need imaging. So this all looks pretty complicated, but basically we're just trying to find a function that is going to minimize the harms. So this term here is representing like the higher cost of missing metastatic cancers. This term here is representing the cost of sending patients for imaging that won't benefit. And this cost-sensitive approach is using this delta factor. So you see a delta here, 1 minus delta here. What's going on with that? Well, the delta is a number between 0 and 1, so weight, that allows us to put, for example, if delta is high, a higher weight on the cost of missing metastatic cancer, and naturally, as a result, a lower weight on the situation where we send patients for imaging that aren't going to benefit. What's the right value of delta? Well, that's not a decision that we could make from an analytics and OR perspective. We did, a search on the different options and then showed this to urologists to weigh in on it. A couple other terms here, if you're interested in machine learning type stuff. We have a regularizing term to help us avoid overfitting. And then this last term is using a Laplacian matrix to estimate the information from those unlabeled patients. So I won't go into a whole lot of detail about this, but the gist of it is, if you imagine that there's a patient that my apologies. If you imagine that there's a patient that didn't get imaged, but they have there are a number of patients that are similar to that patient, nearest neighbor patients, then you try to impute what the impact is and impute, what the likely outcome would have been for that. Hang on. All right, there we go. I'm pretty sure that can wait. So if we were so basically what we're doing is try to impute, what the likely outcome would have been for those patients that weren't imaged. I know I went through that fast, but hopefully you got the gist of it. The last thing I'll say is if we got rid of these regularizing terms, for example, and we got rid of delta and 1 minus delta, we'd be trying to maximize likelihood here. But that's not going to give us the result that we want, because we don't want to treat the different kinds of false positives and false negatives equally. So we tried that approach, but we also threw a lot of ideas like random forests and AdaBoost, support vector machines. Once you do, apply one machine learning approach, it's very easy to apply many, and we're agnostic. All we cared about was getting accurate models. So we tried a lot of different approaches. And there's a lot here, so I'm just going to try to walk you through this. This is the main result sort of from a methodological perspective. So I'll concentrate on CT scan, and you've got bone scan over here, and you can look at that, and we can talk about that in the Q&A if you like. But I'll concentrate on CT scan here. So what are we doing here? Well, we're plotting bias-corrected sensitivity using that bias correction approach, and based on estimates that are using all kinds of different machine learning approaches, including the one that I spent some time talking about. So if you look in the figure, every one of these dots represents the outcome from one of these approaches. And so we've got, what we want to be is up here. We want that perfect guideline that will classify patients with 100% sensitivity and specificity. We can't get there, but we get this trade-off curve. Lots of the approaches, are dominated. So the circles, the green circles, are showing you the non-dominated guidelines. A number of them are that new approach that I mentioned, but some are like AdaBoost or support vector machines. So depending on where you are, different approaches might work better. You can also see that the AUA and the EAU guidelines, they're actually dominated, but they're very close to being Pareto optimal. And they have a lot of backing. These are endorsed by urologists who are obviously extremely knowledgeable about this kind of decision making. So this was actually really important to see that these are close, and they seem to have a good trade-off between sensitivity and specificity based on feedback we've received. But where you lie on this curve of green dots, that's going to depend a lot on the kind of resources you have available in the state you're in or in the country you're in. So there's not a perfect answer about what the right trade-off is, but these seem to give a good trade-off relative to importance of these two criteria that are attached to it by urologists in Michigan, and probably many urologists across the U.S. So now I'm going to switch to implementation. So how do we get this stuff implemented? Well, we definitely did not talk to urologists in the collaborative about this graph, because there's so much they don't care about here. Don't care about the blue dots, don't care about the machine learning approach. What they want is good decisions for their patients. And even sensitivity and specificity, these are sort of technical terms. There are lots of urologists that they haven't been using like clinical statistics a whole lot in recent years, and so this needs to be explained very clearly to urologists. And so what we did was we transformed this, essentially the same data, but into something that urologists and patients can understand. And I should mention that there are also patient advocates that were a part of this decision-making process to implement this. So we looked at the percentage of patients with metastatic disease and the number of imaging tests that are done on the x-axis. So two important considerations that are a little closer to the real world, I would say, of what's happening. So what you see here is, first of all, you have to think about like what's acceptable risk for a patient, and that varies a lot. So some actually would say, well, 5% is acceptable. Some would say 4, 3. We got all kinds of numbers. The lowest and most conservative was 1%, and so we're looking at this from the perspective of, okay, what's a guideline that's close to the efficient frontier and has something below 1%. And you can see actually AUA for CT scan, AUA and EAU guidelines are well below 1%. But how, where you land here makes a big difference. So if we said 1%, we could think about how many imaging tests are being done here per 1,000 men versus the AUA guideline or the AU guideline. These don't look like big differences, but they do translate into huge numbers of imaging tests. So we looked at this and we went over this with a focus group, but this is not what we took for final decision. And so what I want you to do is imagine that, okay, you feel very confident about the results that you have. You've done a huge amount of validation. You work with a focus group, you get feedback from patients, and now you want to try to convince a collaborative that involves 42 practices, more than 100 urologists, that this is a good idea. So the way this actually happens with music, it was amazing. And my clinical collaborators are the ones actually developed this. They were the inaugural directors, Jim Monty and David Miller. And we literally went into a room, and I was there as an observer, and my students were there as an observer. And this is the final table, and we just poured over this table forever. But this is a table that was used in a room with more than 60 people in it, many urologists, also nurses, and patient advocates. And we looked at bone scan and CT scan. We never said a word about machine learning. That probably would have done more harm than good. What we did was we extracted guidelines that are based on the actual clinical factors that are extremely close to being on the Pareto, Pareto optimal. And then we did a before and after comparison. So we projected that, for example, if we implemented this new guideline, 22.6% of patients versus 27% of patients would be scanned. So that's fewer scans, but it's not fewer scans for the patients that were already being scanned. It's a different group of patients that are getting imaged now. Okay, so among those that are getting imaged, 14.3% were estimated would have a positive imaging test versus 10% based on the historical data. And we estimated 0.4% of the patients would have missed metastatic disease. So yeah, this was what was literally used to get buy-in. Remember, at this point, we hadn't done the external validation yet, so we had to think about, well, what's acceptable risk here in implementing something, and we had in mind like improvement over the current baseline as being the key thing. So there's literally like virtually unanimous, if not unanimous, it was a number of years ago, but approval of this by urologists. And then after that, a process kicked in that's organized by music with the help of Blue Cross Blue Shield. They didn't just say, hey, these are the guidelines and you have to use them. That would never work. They developed a term that they call appropriateness criteria, intentionally not a guideline or a rule or a requirement. They set a statewide goal that 95% of patients that meet the criteria for imaging would get it, and less than 10% that don't meet it would not get it. And that's critically important. Sometimes people ask, well, why not try to have 100%? Well, that would, if we did that, then we would, be missing things like very important clinical judgment that urologists have. And so whatever that may be, they have the authority to order imaging tests. But there is an incentive to try to achieve this kind of compliance and for this appropriateness criteria, and there's regular reporting to urologists. And this has been going on for more than 5 years now. So I'm just going to wrap up just about another minute or two. A separate independent study was done to validate the approach. There's a publication on it. This is all using data after implementation, well after implementation, which took quite some time. And it's a before and after. So baseline before any of this work was done, post-intervention is after the models and guidelines were implemented. And what we saw was a very substantial reduction in the amount of imaging, okay? You can see very substantial amounts of reduction in the amount of imaging that are done. We expected to see an improvement in the detection rate. And there was an improvement, but it was not statistically significant. So the best way to describe this was we substantially reduced the amount of imaging that's happening and did no harm when it comes to the detection rate relative to the baseline before we did any of this work. So main outcomes, reduction in harm to patient health from reduced radiation exposure, fewer unnecessary follow-up procedures that happen when you send patients to get imaging tests, and lower patient anxiety. Those are the most important things. There's actually cost savings that occurred because ultimately there was less imaging and patients in greater need were getting the imaging. But that wasn't the goal of the project. But nevertheless, there was that. I would argue that the financial savings from unnecessary follow-up procedures probably dwarfs this, but we did not measure that directly. And then we implemented these tools and a number of other tools on a website called Ask Music, and you can check that out if you go to the link or Google Ask Music, and you can see some of those models. And there's a number of other ones that have been developed since this work was done. We published papers in the urology community, and also I mentioned that operations research paper. That's the top one there. And you can learn lots more about all of this stuff if you're interested. Celine Merdan was one of the really heavy lifters. She was a PhD student at the time. In fact, this whole project defined the direction for her PhD. A lot of her dissertation was on this. And Christine Barnett was another PhD student who was very involved in this. David Miller and James Monti, these are the primary, the co-directors of music at the time and the primary clinical collaborators, but there are a huge number of people involved in the music collaborative, too many to mention. So if you're interested in learning any more about that, check out the papers, contact me if you want. Like I said, a big team of people, and not the least of which is this entire music surgery improvement collaborative. Hundreds of people that did an enormous amount of work. The actual modeling piece of this and the stuff I talked about today is that's the easy stuff, once you have the data. The collaborative is doing some incredible things to improve men's health and related to prostate cancer in Michigan. With that, I will thank you for your attention, and I'm happy to answer any questions. In fact, I look forward to it. Thank you.
Hey, thank you, Brian. If you see the Q&A button on your screen, I think there is one couple of questions there, and then we can open it up if people want to ask directly.
Sure, yeah. If we can open it up,
So do you see the Q&A button? If you click on your Q&A button, you should be able to see the two questions submitted. Otherwise, I'll read it to you.
yeah, so I do. I see one from Maureen Appelman, my colleague here at University of Michigan. And so she's asking, how do you estimate the probability that the disease is not present, given that the guideline is negative, meaning that you shouldn't get it, and the probability that the disease is present? And the way you do that is using that logistic regression model I mentioned. So we build it on the population of people that have labels or got imaging, and then you can apply it to the rest of the population. So you can get an estimate of the probability that the disease is present overall, and a probability of this conditional probability that is out there. And actually the approach is fascinating. The biometrics paper, and I'm happy to send this to you, Marina, describes conditions under which this works. It's a little bit surprising because you're applying this model that has some biases associated with it to the overall population. But in this context, assuming you have data that's just missing at random, then it works. And the key thing is that we have access to all the data that's deemed to be informative of whether someone will have a positive outcome or not. So I hope I answered that acceptably. And so another anonymous attendee, yeah, how did you approach the problem of data imbalance, which may be separate from cost-sensitive learning? Yeah, so they're related, but I think I understand what you mean. And so some of the things that we did was to use some approaches where we would, for example, like when we were trying to estimate risk as opposed to just classify well, we'd two approaches, the name has escaped me now, but we basically, they're very straightforward. We would oversample, like sampling with replacement, but oversampling the minority class, or the opposite, sampling with replacement, but undersampling the majority class. And I think we talk about some of that in that OR paper, so there might be some more details there. And a question from my friend John Milne, who I've known for many years. Hi, John. So, yeah, John, as usual, great question. Did you get any surprises, insights from the focus groups? Yeah, I love that you asked that question. I was really nervous. So the focus group I mentioned, these are urologists in music, but not part of our study. So I didn't know them when we went to talk to them. My clinical collaborators knew who they were. But there's also, I think, 2 patient advocates there. And the surprise I got was how comfortable they were with things. I think that I was more stressed out about the fact that we hadn't done external validation on the models and making decisions about what acceptable risk is. They were actually, in fact, the patients were less risk averse. As I recall, 2 things I recall. One was that the level of acceptable risk was higher than I expected. That surprised me, and higher than what the urologist expected. And ultimately, we went with a very tight risk threshold, much lower than was suggested. I can't remember the exact number, but that was proposed. But that was a big surprise. And the other thing was how, like I said, how comfortable they were with this. I remember one of the patient advocates saying, "Oh, it seems like the engineering folks, did a good job at doing all the analysis, so feel comfortable with it." And that was a little bit of a surprise. I expected a little more skepticism, and we did, I think, see, like healthy skepticism, more so from urologists who, like all practitioners, aren't very comfortable with the things they're not used to using. So machine learning, for example, it's just a black box, right? So we used a lot of attention and care to detail about some of those things. I Hope I answered your question there. Okay, John.
Yeah, I think they should be open to all now. Anybody online who wants to ask any questions? Uh, I have one question, Brian. So I think, and maybe I don't know if I got it right or not, but you mentioned in the context of the bias that you are only looking at bias in the guidelines. And I guess I was wondering, what if there is a bias in the doctors themselves as to who they suggest should get the screening, whether it's based on the economic background of their patients or the kind of insurance they have. I don't know if this question makes sense or not.
No, it makes perfect sense. Yeah, one thing we learned is that there are a variety of different approaches that people take, urologists take to making these decisions. And yeah, and some of them are difficult things. Like some urologists will, not push maybe an imaging test as hard, or at least maybe I shouldn't say it that way, but they'll have patients who, $250 copay is going to take food off the table for their kids. And so there's a lot of reasons why, you have to think about like the patient very, very carefully. And that's why there's leeway in the guidelines. What's interesting is when you look at how the decisions are made, I mean, initially, without doing any work, my naive assumption was, well, probably everyone's following the American Urology Association guideline. That's like, the informs of the field, right? And they make, recommendations like this. And that's not the case. There's wide variation in what people were doing. And so after implementing some of this, what you see is much more consistency in terms of decision-making around the recommended guideline, but not perfect. But if you were to look at the before and after, you see far more consistency because you have this sort of data-driven guideline that's got buy-in to it and works well. But there are exceptions, like I mentioned.
Any other question from the audience? Okay, hearing none. Again, just a couple of closing thoughts. Number one, the video recording will be posted fairly shortly, and you should be able to find the link on the Informs Practice webpage. Again, and if there are any suggestions or comments about this webinar series, again, just shoot me an email. My name is there on the practice webpage. And again, definitely feel free to check out the future webinars and register for them as appropriate. And Brian, thank you we love to have your presentation. Thank you for a great presentation. And we really enjoyed it.
It was a pleasure for me too. And if anybody wants to know more about any of this work, please feel free to contact me. I was delighted to be able to be here. So thank you, Rajesh, and thank you, Beth, for your assistance too.